In this lesson, we're going to take a look at how intermolecular forces affect physical properties like dissolving, boiling points, and melting points. So first, we're going to go ahead and review key terminologies, key properties, physical properties, melting points, boiling points, and solubility. And after that, we'll take a look at how these physical properties are affected by intermolecular forces. So let's go ahead and review melting point. So our melting point is the temperature at which a substance will go from a solid to a liquid, so a temperature at which something will melt. The boiling point is a temperature at which something transitions or goes from a liquid to a gas, so basically evaporates. And so to do that, you need to basically add energy. And when you do one of these changes, so a melting or boiling, you are breaking the intermolecular forces as opposed to the intramolecular ones. The other physical property we'll discuss is solubility, and essentially it just means can you dissolve in a solvent or not. So here we have sugar and we have water. We have sugar and salt. Salt was put into the water. Sugar was put into the water. We stirred, and now we no longer see the sugar or salt there. It's still there, but it's just dissolved. So we would say that sugar and salt are soluble in water. So if something dissolves, we say it's soluble. Usually we specify what it's soluble in. So for example, in this case here, sugar and salt are soluble in water. But if we look at sand, we put it in water and we stir, the sand just settles at the bottom. It doesn't become part of the homogeneous mixture. It doesn't become part of the solution, so to speak. So sand would not be soluble in water. The term we use for that is insoluble. So insoluble means does not dissolve in water. And so the whole point of our lesson is going to be to predict whether substances dissolve in water or not, and also to make a reasonable guess as to the boiling points and melting points of substances. Not the specific number, but maybe if I asked you to rank which, between these two or three substances, which one has the highest boiling point or melting point, or which one is more soluble in water. So make some relative guesses to different for various compounds depending on their intermolecular forces. So before this lesson, you should have a good idea of how intermolecular forces work and the type of intermolecular forces that can be found in different molecules. So you should review that lesson with LDF, with hydrogen bonding, dipole-dipole, so on and so forth. So we're going to start off with properties of ionic compounds, and afterwards we'll go into molecular compounds. So for ionic compounds, what I want you to get is that their forces or their properties are explained by electrostatic forces. In other words, the attraction between full ions, right? It's full ions, full, a full plus, a full minus. So in general, because you have these full charges instead of partial charges, like a full Cl minus, a full Na plus, you're going to have some very high melting points for ionic compounds. For example, NaCl, which is just regular table salt, to melt it, you have to get to 800 degrees Celsius. To melt water, it's just 0 degrees Celsius. So ionic compounds will have the higher melting points. If I was comparing two compounds, let's say NaCl versus something covalent like water, NaCl is going to have a higher melting point just because that attraction between the ions is very, very strong compared to just, hydrogen bonding that might exist in H2O. So, this boiling point here is 800 degrees Celsius, whereas this melting point here is 800 degrees Celsius, and the melting point for water is 0 degrees Celsius. And when I say melting point, I mean to go from solid to liquid. So ionic compounds have the highest melting points and boiling points because of their full ion attractions. The other interesting property about ionic compounds is they're usually brittle. So if I were to hit it with a hammer, hit a crystal with a hammer or drop it, it would crack. You'd see the little cracks that sort of form along the crystal. And the reason for that is, again, because of the full ion charges. So here's my ionic crystal. Normally you'll see that you have negative aligned with positive, aligned with negative, aligned with positive, and they're all attracted to each other that way. Now, if I hammer it, that's just the stress is there. If I hit it, I shift the parts of the crystal structure. Notice that I have two of the same charges aligned now. Same thing here, two of the same charges aligned. And so they would repel each other. And that's what's causes the cracking. And that's why they're not malleable and they're not really ductile. And that's because when you cause those charges to align that way, the like charges, they'll repel each other and they'll crack in that fashion. So main point here is that the properties of ionic compounds are determined by their electrostatic forces. Yes, ionic compounds have LDF in them, but the major force that's really holding them together is that ionic force, the attraction between oppositely charged ions. And that very, very strong attraction between full charges is what leads to their very high melting points and boiling points, higher than covalent compounds. And then the charges themselves lead to the crystal overall being very brittle. And so those are the major properties of ionic compounds. Now we're going to go and focus on molecular compounds or covalent compounds with nonmetals in them only. So before we go into practice problems in more details, what I want to focus on first are some general rules of thumb. Generally, the more intermolecular forces you have, or the stronger your forces that you have, the higher your boiling points and melting points are going to be. And that's because you need more energy to move the molecules further apart. When you go from, let's say, liquid, where let's say those two dots are my molecules, this is my liquid, and I want to make them gas, they have to spread farther away from each other. So you have to break the intermolecular forces that exist between them. So essentially, the more of those forces you have, the more energy you need, the higher your melting point is going to be, and the higher your boiling point is going to be. Generally, if you have more forces, stronger intermolecular forces, your substance is more likely to be in what's called a condensed state. You're more likely to be either a liquid or a solid at room temperature. So for example, water is a very small molecule. I'm not going to draw this out in full detail here, but it's a very small molecule. But at room temperature, water is still a liquid. And that's because of its strong hydrogen bond. Now, if you look at something like CO2, CO2 is a bit of a bigger molecule. It weighs a bit more because C weighs more than H, and then there's two O's in there. So CO2 is a bit of a bigger molecule. But the only force that it has in between it is LDF, the London dispersion, because this is a non-polar molecule. And so at room temperature, if you breathe out or you look around you, the carbon dioxide is not liquid. You're not swimming in liquid carbon dioxide. It's gas form. So it's a gas at room temperature just because it only had LDF to break. It didn't require much energy to make this a gas. Whereas water, you have to break the hydrogen bond. And so that's only going to happen at about 100 degrees Celsius. So if we were living at 100 degrees Celsius, then when you turn on the tap, you'd have essentially water that was boiling as it came out, but we're not. So that's why water is liquid, but CO2 is a gas, primarily because of the difference in their forces. Stronger forces in water because it's polar, weaker forces in CO2 because it's non-polar. Don't forget, water also has LDF. It's just the strongest force is the hydrogen bond. So in general, when you're comparing melting points and boiling points of substances, ionic will be the highest first because of its very, very strong full ion charge attractions. Polar covalent will come next with hydrogen bonding capabilities. So if you have OH, NH, or HF, generally the OH hydrogen bonding is going to be higher boiling points or melting points than the NH hydrogen bonding just because it's more polar. So for example, H2O is a higher boiling point than NH3. After that will come your polar covalents without hydrogen bonding. So with just regular dipole-dipole interactions, so without the OH, HF, and NH, generally the more polar is going to be a higher boiling point than the less polar. So when you check those electronegativity differences. And then the smallest boiling points, melting points, lowest ones will be the non-polar covalent compounds because all they have is LDF. They don't have anything in addition to that. The last point to also mention is that generally when you have higher forces or stronger forces in a liquid, for example, it gives that liquid a high surface tension. And so what that means is it's hard to break the surface of that liquid. There's a great video here that goes over that. I'm going to show you a quick little picture to illustrate that concept. And this is a really neat application of surface tension. So we'll go here to our presentation. We saw all these slides here with some images just to show you overall the last point I was bringing up here. Here we have some non-polar compounds, CCl4. And here we have polar compounds. Notice that the non-polar compounds, all they can do is LDF, whereas the polar compounds can do LDF and also, in this case, dipole-dipole. So there's more to break here and stronger forces to break here than there are here. So this may have a higher boiling point than, let's say, this one over here, just because over here you're just dealing with breaking LDF, whereas here you have to break the LDF, but also the stronger dipole-dipole that exists between the partially negative chlorine of this one and the partially positive hydrogen of this one over here. So just to show you that surface tension concept, right here we have an insect called the water strider, and it's walking on water. You can see these are its legs there, and it's not breaking through the surface of the water. And that's because the water has some very strong intermolecular forces. There's LDF, which is really weak, but there's also very strong hydrogen bonding. And that hydrogen bonding makes it difficult for that insect to break through the surface of the water. And if it's careful, it'll walk on the water without breaking through that surface. And so that's what is meant by a high or strong surface tension. It's hard to break through the surface of the water because of these stronger intermolecular forces that are there. If you want for additional enrichment or learning about this concept, you can read a little article here with a great interactive quiz about surface tension and a great connection to biology. So for the remaining parts, or for the next videos, we're going to go through some sample problems. We're going to compare molecules to each other in terms of their boiling points and melting points. We'll start off by comparing only nonpolar to each other, and then afterwards we'll step it up and compare polars to nonpolars and do a variety of different types of comparisons. But you'll see that at the end of the day, it all becomes very straightforward if you understand your polarity versus nonpolar and understand what type of intermolecular forces the different types of substances can have.